All right, let me introduce. Today we have, for Keeping Current, Seth Parker, who has been around for a while. He was a student of mine actually in my compiler construction course, as I recall. And he will be talking about a project that he's been involved in recently, metadata-enabled computational graphs, which I hope we will find out what they are because I haven't a foggiest idea. So take it away, Seth.
All right, thank you, Dr. Finkel. Yes, so I am here to talk about metadata-enabled computational graphs, as you see on your screen. We will dive into what those are, but broadly, I just want to introduce myself. I've been here in the Marksbury building for about 10 years now, and I work with Dr. Seals on his research project, and we've sort of recently been renamed the EDUCE Lab, sort of going forward to sort of encompass what we work on. The idea is that we focus on trying to digitally restore damaged artifacts, historical artifacts, cultural heritage objects for the world writ large. One of our major projects is a project known as Virtual Unwrapping. And broadly speaking, because we don't want to get too deep into what that is, Virtual Unwrapping is just a process for reading inside closed books. We CT scan books, and then we perform a bunch of computational tasks, and what comes out are 2D images of the internal pages of a book, or scroll or damaged manuscript of some form. And the motivation behind the project I'm talking about today is that this virtual unwrapping process has many intermediate steps. It's a complicated thing, and depending on the object you're working on, those steps change. For instance, the process that we generally follow is here on the right, and you can see the texturing step in the middle. That texturing step depends upon the chemistry of the ink of the manuscript that you're looking at. So you can't just, run a default pipeline on it and expect a good result. There's a lot of time spent sort of tweaking your pipeline to make it produce decent results. And the principle here, though, is that in this process, we have a chain of decisions that get made that end up producing a final result. And we refer to this as the digital provenance chain, by which we mean any end image that we produce has a chain of things prior to it from the original CT scan that lead into the result that we get. And we need to keep track of this. It's very important to keep track of this for scholarship, because we're basically claiming with our process that we can take a book that no one has ever opened, and we'll let you read it. And you just have to trust us that the text we're showing you is real, because you can't physically open it. So if we don't have this chain, this sort of verified computational pipeline in place, I could make up any historical text I want, and you just have to take it on face value that it exists. But at least with the digital provenance chain, you have some sort of method of like backing up through the process and saying, no, actually you've introduced something here that wasn't actually there in the original data. So that's what we're trying to get at. However, these are highly complex processes, and we want this to be automatic and easy to use for our programmers. So that's sort of what the motivation is for me, is I want to instrument our existing software with, or existing pipelines with this sort of automatic metadata tracking, and maybe also just improve what it's like to build these pipelines. Also looking forward, we're moving beyond virtual unwrapping. We have machine learning elements and image registration elements and code bases from outside of our control that we're using that we would like to also instrument with all of this automatic metadata tracking. And so there's a bidirectional thing here that needs to happen, and whatever the thing I'm about to show you does, it needs to sort of be able to support those things going forward. So a couple of goals that we want to address today are, we want to create repeatable data flow pipelines. And so what I'm showing you here is an example of that as a graph. This is an example of adding numbers and then multiplying them and then adding them again to produce a final result, 7 on the end. We want to be able to construct a graph, save it out in such a way that we can reload it and re-verify that the result we get when we run it again matches our original result. So just repeatable data flow pipelines. Our metadata that we produce should be in a nice open format. We don't want people to have to build a custom library or use our custom library just to observe the metadata that we produce. So in this, we've just sort of focused on JSON as a nice intermediate object format that we can serialize to. But you could use any sort of intermediate metadata format, I suppose. And just to introduce this logo on the left here, this is the logo for our software volume cartographer, which is sort of our implementation of virtual unwrapping software. It's used a couple of times in here. So volume cartographer to JSON. And then as sort of secondary goals, we want to be interoperable with our own custom code libraries. Some of these are in C++. Eventually, we'd like to work with some of our Python libraries. All of our machine learning efforts are in Python, as they all are pretty much these days. And then we have some other toolkits that we're using that are C++ that we'd like to use. We also rely heavily on other external libraries, and we'd like a way to use that functionality with sort of minimal effort. Instrumenting, OpenCV functions for our use would be very, very helpful. And finally, we want to support visualization of this metadata. So a thing I just found today is this nice node editor that's built inside of Qt or Qt. And it's a good example of one thing that we'd like to build, is a way of constructing these pipelines in an interactive way, but in a way that also shows you the metadata that you're working with. Okay. And finally, of course, all good projects need to have a great name that's an elaborate acronym. And if anyone knows how Dr. Seals names his research projects, they're always elaborate acronyms. So today we're going with smeagol, the Structured Metadata Engine and Graph Objects Library. So what is smeagol? It is a C++ 14 library for creating graph processing pipelines. And by graphs, I specifically mean directed acyclical graphs, because things get weird when you have cycles and you're trying to do computational pipelines. But for now, it's a directed acyclical graph. And we want to enable opt-in behaviors for computation and metadata. And I'll show you what that means when we get into it. But specifically, we want users to be able to create computational nodes and link them all up to make a graph. And when you run the graph, everything updates automatically. And intermediate results and things are sort of cached and on disk. And you have all these nice behaviors that respond to that. But we also don't want people to have to do that if they don't need to. There are parts of the library that are opt-in for that specific reason. Dependencies, I've tried to keep it very minimal. We use CMake for our build system on pretty much everything at the moment, C++ wise. JSON for modern C++ is an excellent JSON serialization library that's header only and is just excellent all across the board. So if you need any sort of JSON serialization processes, highly suggest this library. And then because we're writing to disk, we use some sort of file system library. These days with C++ 17, you have standard file system, but because we're trying to target C++ 14 at the moment, it also falls back to boost file system in the absence of standard file system. And then if you want to run our tests, you need Google Test, but that of course is optional. So some terminology, computation is performed by a node. So the node that you see here, a sum node, just takes a left-hand side and a right-hand side and produces a result. The circles that you see drawn on the node, these are ports, and data is shared between nodes via ports. And on our left, we have input ports, and on our right, we have output ports. And these are, because we're in C++, these are typed data ports. They take a single type and they produce a single type in the case of input ports and output ports. And then you connect nodes together in order to form a graph. So if I were going to create a graph of this function, g of x, y, z, you can read the definition of that there. This would be sort of the graph representation. You'd have your inputs, x and y, and z, and then a sum node, a multiplication node, and a sum node, which would produce the final result. And when all connected together, you'd produce this final result. One thing that we want to note is that you have some output ports that are producing values for multiple input ports. So this output can go to this sum node and this sum node. Anything that accepts the output type of this, we want to sort of enable that, because In real computational pipelines, you have intermediate results that are often shared between multiple processes. And especially in our virtual unwrapping process, that is true. So we want to enable that behavior. So I'm just going to walk through how this library is used. And so you can sort of get a feel from it. And hopefully we'll talk about some of the weird technical things you have to deal with when you're making something like this. So first, let's talk about just declaring an input port. An input port accepts a value of a particular type, in this case, an integer. It's templated on an integer. And it places that value into some other sort of target. In this case, we're going to place it into this value integer that we have here, val integer. And you declare that by making an input port of a particular type, and you just give it the reference to the thing that to the target that you want. And when you query the input port, or when you give the input port a value, it assigns it to the target that you give it. Targets, it posts a value is the way that the terminology that I use. Targets don't just have to be objects like you see here. They can be functions, references to functions and things like that, and that's where the real behavior becomes important. When you declare an output port, it's a very similar nomenclature. But rather than, or you're still templating on a type that you now produce, that this port is going to give you if you ask it for its value. And you give it a reference to the thing that it's going to read from when you query it for a value. So in this case, whatever the value of val is will be produced when we query it. So if we compare these two things, these will compare to true. So we're going to get the port's current value from its source, which again can be functions that return a value of type int in this case. This is really flexible, as I mentioned, in that you can support anything that can be converted to a standard function. And if you're not familiar with the standard function, it's a really excellent way of encapsulating function references, so to speak, as a type or as an object in C++. So lots of things can be converted to standard functions sort of implicitly. A reference to a function can be implicitly converted to one. In this case, we're an input port and we've templated on int, so it will accept any function reference that has an int as an argument, a single integer as an argument. For output ports, it's templated on the return type, so any function that returns an integer can be used in this manner. You can also do the same with member function references. You give it the object and the reference to that object's member function, and that would also be acceptable. Or you can do everyone's favorite and give it a lambda function. In this particular case, I've given it a lambda function with a context of this object bar here that I've created. And I'm doing the work inside of that. So those are all sort of flexible ways in which you can construct the targets or the sources for your input ports or output ports. To make a node then, we just use our input ports. And the very first thing we need to do is just inherit from a node class, a generic node class that our library provides, smeagol provides. Here in the private, you just have some setup for the targets and the sources that we'll be using. Result is just an intermediate cached value that I initialize with these things that's not going to stay that way. And then I add my ports to the public interface for the node, which I'm not sure if I like at the moment, but that's what happens at the moment. And we just connect them up to the input ports to their targets and the output port from its source. In our constructor, we need to register input ports, which is a bit of boilerplate that I'm still thinking about how to get around. But essentially, this is just saying at some point in the future, you'll see we'll need to know what ports are, but we can't actually know their names, but we don't actually know what type they're supposed to produce. This is a very big, hard problem in serialization and deserialization inside of C++. So right now we're just declaring that these things have a name, a generic string name, and this is how you access them. And then we're going to define our compute behavior. Compute is it's actually a protected member of the node class, and it is a standard function that takes no arguments and returns void. So as long as as long as it doesn't require arguments, you can do any sort of function you want. You can assign any sort of function to this that you want. In this case, I'm doing a lambda function where I take the context of this class and I assign to the result the left-hand side and the right-hand side. And that's sort of what our computation means for this. And I could stop right there. If I just wanted to make a bunch of numerical operations that don't rely on serialization or deserialization, this is the minimum that I need at the moment, is just this compute function and these registered ports. And actually, if we don't care about serialization, or we don't even really need to register the ports, I don't believe. I have to think about that actually. But yeah, so this is sort of the minimum for a node. If we want, and this is sort of the final class, and I do want to note, again, you can use existing functions rather than, or existing functions and references rather than relying on lambdas or anything like that. We can do member references, or I provide this wrap function, which is really just a syntactic sugar around getting a member function reference and calling compute with that. So I wanted the interface to use this to be very simple in terms of just how we declare these nodes. If we want to go a step further and serialize, we do have sort of in the base class node a serialized, deserialized virtual function that needs to be overridden by our implementing class. So in this case, serialize has a bool value that tells us that, yes, we want to write to, we're going to have a cache directory somewhere and we want to write to it right now. So if you have any disk write operations you need to do to cache values, go ahead and do that. And then here is the directory, the path to the cache directory that you can write to. So whatever you need to do, use this directory. And then the nomenclature for most serialization, though, you don't actually need to write things to disk. You really just need to keep a string value of your result in some form. And in JSON, there are lots of sort of implicit types that can be written integers and floats and things like that. So the way you construct that is you're really just constructing a map, a key value map here, where left-hand side, you're going to use the value of your private left-hand side variable, same for right-hand side and same for result. And we just sort of return that, and the smeagol library takes care of writing that to the actual JSON file. And for deserialize, we just do the inverse. We're going to get the metadata file that we produced before, or the metadata structure we produced before, and the path to the cache directory. And we load from our metadata file using the keys that we previously defined. And our cache directory, if we need to read anything from that, we can do that as well. Building a graph, we're gonna just build that graph that we saw before. It looks something like this. We make shared pointers to our nodes. And in this case, our integer nodes are gonna set their initial values to 1, 1, and 3. And then we make nodes for our different operations, also as shared pointers. We connect our nodes. So this first two connections are just connecting our x get value and our y get value to our sum, one in left-hand side, right-hand side. And then we want to connect our z value to our multiplication and our result of the sum to our multiplication. And then we're going to get the result from multiplication and add it to our second sum, and our y value and add it to our second sum as well. To build a graph, you just initially create a graph object, insert your nodes, either individually, you can do this as you construct them, or you can just insert them all as you see here. And then you just call update on it. And if you were to query the result value of our final sum, it would give you 7. And then if you make some changes to your nodes, depending on the inputs that you want, so in this case, I've changed y and z to 2 and 4. That would also, when you update the graph, it would update the result. So this is the graph processing part. Because we use node factories to sort of write and read nodes, you have to register them with the factory. So that's also a bit of boilerplate that we have at the moment. But essentially, you just call this function register node with the types of the nodes that you want the serialization to know about. You do save it to whatever file path you want, in this case graph.json, and then you can load it from the same. And at the moment, this graph is a new instance. All the nodes are identical in properties and connections and things like that, but they are actually different instances. And so I haven't quite gotten around that yet. What you'd really like is when you reload a graph, if nodes are identical, and I mean universally unique, which is something we have to find, then you just use the existing instance rather than you know, having to construct a copy, so to speak. So that's something that needs to happen, but at the moment it works. And the output in our JSON file for just one node looks something like this. We have a generic type name, and this is what we use to deserialize. A unique ID, we do use the actual, what was it, RFC 4122 UUIDs. These are actually completely random, randomly generated, as opposed to some UUIDs are generated from the timestamp or things like that. These are completely random. Input ports also have UUIDs, although I'm not entirely sure we need them, but right now they do. And then the data that we wrote in our serialize method is sort of cached here in this nice object. So one of the challenges with the serialization in C++, and I want to mention this because I think it might be useful for other people, is how do you name your nodes for serialization in such a way that you can load them back easily, deserialize them easy. So how do we get this smeagol sum node here from just calling register node? So a lot of the time in the factory registration pattern, people will do manual naming, by which, and you can do this inside of smeagol as well. When you register a node, you just tell the library, I want you to call it this. I want to call it sum node. In our factory, if you want to create one of those, you give it that string and it produces a generic node pointer of our base class. But the pointed to object is actually one of our sum nodes. The problem here, I mean, it's a problem, not a problem. One of the things that's not super nice about it is that you have to call this register node function at some point. And if you're writing a library of these sort of nodes, it's an easy mistake to have to manually type this in and to get a result that you're not expecting. So this is doable and we do support it, but you would like it to be a little bit nicer. So another way, or you'd like the programmer to not have to type as much. So one way you could do it is you could have a member function to your node that you override that provides whatever its type name should be. So now you're only writing it in one place and you call register node and it knows, it calls this type name function when it's serializing to write out the correct node type. So that's one nice, but there is a problem with this construct too. And I hit it fairly fast actually writing that sum node, which is we can template nodes. So a sum node is not just good for an integer type, it's good for a floating point type and any numerical type. And now the thing is our type name function doesn't really know anything about the template type. There's not a good way to convert a template type to a sort of fun, like a stringified version of that. In sort of a nice way. So that's not great. You don't want the programmer to have to like figure this part out. If I register a sum node on an integer and a sub node on a float, and then I want to create one, what do I call to create one? So that's not a great solution. You could, of course, just give them all a unique name, some int node, some float node. That is a lot of like typing in the registration code again that we wanted to avoid. And anyway, I've already named them, right? They're in my library and they're called smeagol namespace sum node with an integer template and smeagol sum node float with an integer template. So it'd be really nice if we could get access to this. And it turns out in certain compilers you can. So we actually use auto naming. So there is, if you're unfamiliar with the concept of RTTI, runtime type information, there is a way in standard C++ that you can query what type a pointer or a member, object reference or an object pointer is, what its fundamental type is. So even if it's inherited from something, you can find out what its type is, and you can even ask it for its name. The problem is the name is implementation defined. So depending on whether in GCC or Clang or some other compiler, it's not generic across compilers. And so if you serialize using that name directly, then you can't ever deserialize on a platform, on a different platform, or a version of Smeagol that was compiled with a different compiler. So that's sort of a problem, but there is, I learned during this project, a C++ ABI, an application binary interface, which specifies how compilers are supposed to construct their binary files so that they can be interoperable. So for instance, you can compile in Clang, but link against code that was compiled with GCC. And that's all because they sort of follow this ABI, Titanium C++ ABI. And what's really nice is that that ABI actually provides a demangling method. So you can give it the type info, the RTTI type info name, and it can convert that to the actual like declared object name that you came up with in your code. So in our graph.json, you actually end up with this nice sort of templated type that actually is sort of portable across systems. I say kind of is portable though, because the ABI, as I note down here, is only implemented in certain compilers. It's definitely in GCC and Clang. It's in others as well, but it's not in the Microsoft visual compilers. So that's C compiler. So that's not super great. And I'm still sort of thinking about how to get that around this in the long run. But at least for now, this is a nice generic way to handle template types. And for our immediate purposes, we don't have any code that's running on Windows at the moment. So it's not a huge issue for us. And if you want to see example code of like how you demangle these names like this, I provided the Stack Overflow link, which is where I found it. It's very, very fascinating. So we have a test case that I wanted to just use this on in real life, and it actually helped me fix a bunch of bugs in my code. And it's our volume cartographer application. So I went to one of our more complex programs, our rendering program, by which we actually generate our 2D images. And I wrapped all of that functionality into new node types and added the deserialized, serialized stuff, and I rebuilt the graph, rebuilt it as a graph. And just so you can see the complexity of this graph, this is sort of what it looks like for us, the number of operations that we do. Some of these are just sort of helper nodes. So for instance, we have a central data structure that we call a volume package, and it provides some things like a segmentation or a CT volume and things like that. So there's some helpers here that aren't really there in sort of the original construction. But we do have some meshing operations that get shared, their output gets shared. So the mesh that gets generated here gets flattened over here, and it gets written out as an OBJ file at the end. And then this UV map, this flattened UV map that comes out of this flattened mesh, gets used to produce another intermediate file that we call a PPM, which is really just a data structure we use to accelerate our process. But that also needs to be written to the OBJ file when we want to make a textured OBJ. And then we also have a composite texturing. This is the method whereby we actually generate the text that we look at in a virtual unwrapping result, and we want to cache results from that as well. So this is relatively simple, but still complex pipeline. Let me exit out of the presentation mode here. Hope you can all still see my screen with my code and my terminal.
Yes, it's fine.
Excellent. So the code looks something like this. We have a class for doing different operations, loading a mesh, inherits from node, and we keep a bunch of intermediate types. Typically, these intermediate values are things that we end up needing to serialize later, like our path value here. Or it's some object that needs to do work. So we want to just keep one instance of that around. So our reader object here. Our input port, this is a good example. Because I need to serialize path, I want to remember where that goes, where that points to. I'm using a Lambda function, and I assign to path, and then I set the reader's path function, because my reader object doesn't have a get path function. So, which is probably a blind spot in our API, but whatever. Anyway, so then I get my other output ports, which use the reader, and just get its member function output functions, its get functions. Wrap all of that up and serialize and deserialize, and that's basically it. Come down to one of the texturing nodes. So this, I mean, this is 600 lines of code, and you can see it has a bunch of boilerplate that you'd like to avoid. And I'm, again, if part of my reason in doing this presentation is I would like some feedback maybe from people if they have ideas about how to reduce boilerplate in these circumstances. But most of this code is just boilerplate reconnecting our nodes, wrapping existing functionality into nodes. I could, if I wanted to, go take my existing classes and inherit from node directly and re-implement all my get and set functions as input ports and output ports. That is totally doable. I wanted, before my test, I didn't want to do that. But you could just implement your library as a first class sort of smeagol graph if you wanted to. And you would avoid maybe repeating some of the stuff that we're doing here. And just at the end, this is how I handle registering nodes right now. I just have one function that gets called at the beginning of my actual executable that does all my registration for me. There are methods of auto-registering nodes when you import them in the first place. They're not super portable if you're building static libraries, which is a little disappointing. You know, there are ways sort of that you could improve upon this with macros or things like that. So one of my personal goals in this is I wanted to never use a macro if I could avoid it. And thus far I have succeeded. Mostly because I just find macros sometimes incredibly confusing. Sometimes they're very helpful, but my goal is to not use them. If I run this program, it's running here in this, I get a graph directory that gets created, and for every one of my nodes, I get a cache directory that is its unique ID. And as my code runs over here, new directories get made, and inside certain one of these, you'll find the intermediate files that we've produced. Some of them don't have intermediates. But the whole idea here is that now that this graph has been generated and saved, I can reload this from disk. And not only can I rerun it if I want, but if nothing has changed in my graph and I tell it to update, it doesn't actually have to do any work. I've cached all the results. And so, yeah, you sort of optimize for the future. If I want to just go to that last node in my graph and change some of the parameters about how I generate the texture image, I don't want to have to regenerate everything prior to that, which as of right now, we have to do. So this caching of intermediate results is super, super powerful for us, and makes sort of the back and forth between finding a good result and tweaking that result makes that go a lot faster. And then finally, my program writes out the final result. We'll load it up, why not? This is just a test data set I have that has a simple plane, and that plane has the lorem ipsum text on it, if you're familiar with the lorem ipsum text. So that is my result. So back to presentation here. All right, so what's sort of next is we're generally moving within our group to be more open with our source code. We've had some source code that we've worked on for a really long time, and it's been sort of hard to like get adoption, obviously, because we want, we've been wanting to perfect it or to sort of get our best result before we release it. But really, we're just realizing it's better to just go ahead and release if we're eventually going to anyway, and let other people benefit or help them help us improve what we have. I think, and this is a perfect circumstance, I think, for that, where I have a very clear vision of what I need this to do, but I'm also not sort of a graph processing expert. I don't really know a ton about that part of sort of the literature. And so having other people help with that, or having other people say, hey, here's our use case, how can we sort of improve this library overall, is going to be really good. So I would expect in the next, by the end of the semester, I'll have this online somewhere in an open source way that people can use. The only reason it's not yet is I literally got the graph processing part done on Monday. So it needs a little bit of cleanup even by my standard before it gets released. But if anyone's interested in using this library, let me know, because we do want it to be open. Reducing boilerplate, I've echoed that multiple times throughout. Boilerplate is just a pain when you're building huge libraries and huge computational processes. So as much as that can be reduced, the better. I think there are probably improvements to the interface that can be made, just simplifying things that right now take multiple steps. That goes along with reducing boilerplate. User-defined metadata. In our particular circumstance, we have metadata about the objects that we're working on that we also need to sort of keep alongside the graph. And so just having some sort of way to have a user specify a section of our graph sort of output JSON file that's user defined would be really nice. Parallel processing, once you start having things in graphs, this left-hand side of this graph, this selecting the volume up until composite texture, is independent of this right-hand side of the graph up until about here. So you should be able to do whatever this left-hand side work is and whatever this work is at the same time that all of this is going on. So parallel processing, multi-threading, that sort of thing, that support would be nice. Right now, I just use Dept for search to sort of schedule the nodes in the correct order, which is why it needs to be an acyclical graph. There are of course many different scheduling algorithms that could be implemented here. And finally, visualization. I mentioned before that I haven't really gotten to visualization yet, but you want to be able to visualize this graph, not only the structure of it, but also the encoded metadata and the encoded cache data. And so I think, keeping with the smeagol name, the only appropriate course of action is to have a new library called the Graph Observation Library for looking at underlying metadata, or Golem. So, any questions?
Well, thank you, Seth. I have one, I don't know if it's a question or a suggestion. My first inclination to remove all that boilerplate would be to have a preprocessor. You don't like macros, but maybe you would like to develop a specific smeagol front-end language that then generates what you just showed us with all of the boilerplate in place, but that wouldn't be necessary in the front end at all.
That's a good point, actually. The Qt library, the Qt graphical user interface library, it actually does kind of that. It adds extra keywords and things to C++, and then they have a pre-processing function that generates code for you. And actually, I'd been avoiding Qt because I didn't want to be locked into their keywords. But actually, it might actually make a good, you're right, that would be a good way around some of this.
I have also a comment. It's similar to what Dr. Finkel said. In bioinformatics, you have often web-based platforms to put together, a graph for a pipeline like you are building. So it might be also a good reference to look at a couple of solutions in bioinformatics. It is just a level above, so you already have a graph processor or you are finishing it. It would be just moving it to a more convenient interface for the users.
Yeah, that's definitely true. The one thing I still haven't quite wrapped my head around with the C++ part of this is, because C++ is so strongly typed and statically typed, having a user make a novel graph directly with the C++ code is a little bit painful. So a web user interface, and I'll look at bioinformatics, that's a really good point. I'll look at what sort of platforms are. That's great.
I have a question that maybe I was maybe a minute or two late. So maybe you mentioned something about that. Your flowcharts don't have branching instructions, do they? Is that
No.
branching?
I'm sorry, you cut out. What did you say?
Branching, branching.
No.
Is it needed or is it not needed?
I don't think so. The way that it's sort of implemented right now is our output ports just sort of keep a reference to the thing that they're supposed to update. So once they get a new value, they just directly call that function that they've sort of kept a reference to. So there's not really any sort of, beyond just that, keeping a list of what things it's connected to. It doesn't really keep any other metadata or anything like that.
So in other words, things that happen later never depend on the outcomes of what happened earlier.
They do. They do depend on the previous outcomes. But we handle that by passing values, basically.
Okay.
So when I get a new value, then I can re-update rather than sort of needing to know the structure before. So that's where the scheduling actually becomes more important, because if I don't execute them, of course, in the right order, then my values are wrong by the time I get to them. So does that make sense? Does that answer your question?
Well, I cannot say if it does. I know too little about what you presented today, but I can see other ways to handle that.
Okay.
Along the lines that you've explained.
Okay. Anybody else?
Well, if there are no more questions, I'm sure that people can ask you offline, since you are available in the Marksbury building, or by telephone for those who aren't coming in, or Zoom in other ways. So thank you very much for an interesting presentation. It's good to see that C++ has a future, although people have mostly, as you pointed out, moved on to other languages like Python. But very nice to see this, and to see some of the facilities that the most recent versions of C++ has that you're certainly taking advantage of. So let me tell everyone to stay current, keep current. Hope to see you in coming weeks. And please volunteer to speak, because we have a fairly open schedule. The schedule, if you want to know where it is, it's send me email, but I often send out in my weekly announcements where the schedule is. So see you next week, I hope. And thank you all for joining.